Everything we thought we knew about the world's tallest mountains was wrong. For more than 100 years, scientists have been confidently explaining how the mighty Himalayas stay standing. But here's the shocking truth. They've been fundamentally mistaken about what's actually holding up these colossal peaks. Imagine discovering that the foundation of your house isn't what you thought it was for over a century. That's exactly what's happening in the world of geology right now, and it's turning our understanding of mountain formation completely upside down. The traditional explanation that's now crumbling. Since the early 1900s, the scientific community has rallied behind a seemingly logical explanation for the Himalayas' extraordinary heights. The prevailing wisdom suggested that these towering giants, along with the expansive Tibetan Plateau, owe their existence to a phenomenon called crustal doubling. This theory, first proposed by Swiss geologist Emil Argand back in 1924, painted a straightforward picture. When the Indian tectonic plate crashed into the Asian plate, the collision caused Earth's crust to fold and thicken dramatically. Scientists calculated that this process created a crustal layer stretching down an impressive 45 to 50 miles, roughly 70 to 80 kilometers below the surface. The logic seemed bulletproof at first glance. After all, if you want to support something as massive as the Himalayas, you'd need an equally substantial foundation, right? For decades, this explanation satisfied both researchers and textbooks worldwide. But here's where it gets controversial. The fatal flaw that scientists ignored. There was always a glaring problem with this crustal thickening theory, but the scientific community seemed content to overlook it. Deep beneath the Earth's surface, temperatures climbed to extreme levels. As you venture deeper into that supposedly supportive thick crust, the intense heat transforms solid rock into something entirely different. Pietro Sterni, the brilliant geophysicist leading this groundbreaking research at the University of Milano Bicocca, puts it in terms anyone can understand. If you've got 70 kilometers of crust, then the lowermost part becomes ductile. It becomes like yogurt, and you can't build a mountain on top of yogurt. This yogurt analogy might sound amusing, but it reveals a devastating weakness in the century-old theory. At approximately 25 miles, 40 kilometers down, the crustal material becomes so soft and pliable that it loses its structural integrity. Essentially, the foundation that was supposed to be holding up the world's tallest mountains would be as stable as dairy product. How did the scientific community miss this obvious contradiction for so long? And this is the part most people miss. The game-changing discovery that's rewriting geology. Sterni and his research team have uncovered something extraordinary that challenges everything we thought we knew. Their revolutionary findings suggest that there's been a hidden player in this geological drama all along, the Earth's mantle. Unlike the traditional model that imagined just two crustal layers pressing together, the new research reveals a far more complex and fascinating structure. When the Indian plate dove beneath the Eurasian plate millions of years ago, something unexpected happened. Instead of the mantle material simply flowing away as previously assumed, portions of it actually got trapped and squeezed upward. Picture this. Chunks of mantle material became sandwiched between the two crustal layers, creating what researchers now call a mantle sandwich. This additional layer provides something the crust alone never could: genuine structural support that doesn't turn into yogurt-like mush under extreme temperatures. The mantle material doesn't liquefy at the same temperature as the crust, and this layer of mantle adds strength to the region, Sterni explains. This means the Himalayas aren't just sitting on a foundation of doubled crust, but rather on a sophisticated three-layer system that combines the best properties of both crustal and mantle materials. Simone Piglia, who collaborated on this groundbreaking study, captures the excitement of this revelation perfectly. Things actually start to make sense now. Observations that seem to be enigmatic are actually now more easily explained by having a model where you have crust, mantle, crust. Why this discovery changes everything. The implications of this revelation extend far beyond just understanding one mountain range. For over a century, every piece of geological data from the Himalayan region has been interpreted through the flawed lens of the double crust theory. As Sterne points out, historically, any data that would come along would be interpreted in terms of a single, double-thickness crustal layer. Now, with this new three-layer model, previously puzzling seismic readings and geological observations suddenly make perfect sense. It's like finally finding the missing piece of a jigsaw puzzle that scientists didn't even realize was missing. But here's what should really keep geologists awake at night. If we were this wrong about the Himalayas, what else might we be missing? This discovery opens up a Pandora's box of questions about mountain formation worldwide. Could other major mountain ranges like the Andes, the Alps, or the Rockies have similar hidden mantle structures? How many geological textbooks will need to be rewritten? The controversial questions we need to ask. This breakthrough forces us to confront some uncomfortable truths about scientific certainty. How could an entire field of study be so confident in a theory that had such an obvious flaw? Were scientists simply too invested in the traditional explanation to question its fundamental assumptions? Moreover, this discovery raises fascinating questions about the dynamic nature of our planet. If mantle material can be squeezed between crustal layers in one location, where else might this be happening? Could this mechanism be actively shaping other regions of our planet that we haven't yet identified? Perhaps most intriguingly, this finding suggests that the Earth's interior is far more dynamic and complex than we previously imagined. The idea that chunks of mantle can be pushed upward and trapped between crustal layers paints a picture of our planet as a far more active and intricate system than the relatively simple models we've been using. What do you think? Are you convinced by this new explanation, or do you think there might be even more surprises waiting to be discovered beneath the world's highest peaks? Could this discovery be just the tip of the iceberg in terms of what we don't understand about mountain formation? Share your thoughts and let's debate whether science moves too slowly to question established theories, or if this kind of revolutionary thinking is exactly what we need more of in geological research.